Right now, somewhere in the darkness between the stars, an object is travelling toward our solar system. It's been journeying for millions of years, carrying within its structure the chemical fingerprints of a distant world we've never seen. Tonight, as you listen to these words, that visitor might already be close enough for our telescopes to detect. A faint point of light moving against the stellar background at speeds that would make your head spin. But here's the thing about finding visitors from other star systems. They don't announce their arrival. They don't slow down to say hello. They race through our cosmic neighbourhood at velocities so extreme that by the time we notice them, we have only weeks or months to study these messengers from the depths of space before they vanish back into the interstellar void, taking their secrets with them. Like and subscribe to embark on this cosmic investigation, and leave a comment with where you're listening from. The journey begins now. This is the story of humanity's ongoing watch for the next interstellar object, a quiet but intense scientific hunt happening right now across observatories on 6 continents. It's a story about astronomers who spend their nights scanning the sky for something that shouldn't be there, something moving too fast, something that doesn't belong to our solar system. And it's about the growing realization that these cosmic wanderers might be far more common than we ever imagined. The hunt began in earnest on October 19, 2017, when a telescope in Hawaii detected something extraordinary. The object was small, dark, and tumbling end over end as it raced away from the sun at 87,000 miles per hour. When astronomers calculated its trajectory, they discovered something unprecedented. This wasn't a comet or asteroid from our solar system. This visitor, which they named Oumuamua, had come from somewhere else entirely, the first confirmed interstellar object ever detected passing through our cosmic neighbourhood. For 6 weeks, telescopes around the world tracked Oumuamua as it sped toward the outer solar system. What they found defied easy explanation. The object was unlike anything in our astronomical databases. Long and thin, tumbling chaotically, showing no signs of the gas and dust emissions that characterize normal comets. Most puzzling of all, Oumuamua was accelerating slightly as it moved away from the sun, a phenomenon that couldn't be explained by gravitational forces alone. 2 years later, in August 2019, amateur astronomer Gennady Borisov spotted another interstellar visitor through his telescope in Crimea. This second object, designated 2I Borisov, behaved more like a conventional comet, developing a bright coma and tail as solar radiation vaporized ice from its surface. But even Borisov held surprises. Its chemical composition was unlike any comet from our solar system, suggesting it had formed under very different conditions around an alien star. Then came July 1st, 2025, when the Atlas telescope system in Chile detected the fastest interstellar visitor yet discovered. Racing through space at 130,000 miles per hour, 3I Atlas was moving nearly twice as fast as its predecessors. This third interstellar object was also the largest and brightest yet found, giving astronomers their best opportunity to study material from another stellar system in unprecedented detail. But 3I Atlas brought its own mysteries. Early observations revealed unusual dust properties and selective outgassing patterns that didn't match conventional models of cometary behaviour. The object's trajectory was also puzzling, arriving nearly parallel to the plane of our solar system, rather than diving down from above or below, like most interstellar wanderers. Some researchers began asking uncomfortable questions about whether all the properties they were observing could be explained by natural processes alone. Now, as 3I Atlas fades from view on its journey back to interstellar space, astronomers are preparing for the next visitor. And they're not waiting passively. Around the world, a network of increasingly sophisticated detection systems is scanning the sky every night, searching for the telltale signs of movement that might herald another messenger from the stars. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, operates 4 telescopes across Hawaii, Chile, and South Africa. These automated sentinels scan the entire visible sky several times each night, photographing millions of stars and galaxies in search of anything that moves or changes brightness. The system was originally designed to spot potentially dangerous asteroids heading toward Earth, but it's proven remarkably effective at detecting interstellar visitors as well. Dr. John Tonry from the University of Hawaii, who leads the Atlas project, describes the challenge of finding interstellar objects among the countless points of light in each night's observations. The software has to distinguish between the motion of ordinary asteroids and comets, which follow predictable elliptical orbits around the Sun, and the hyperbolic trajectories of true interstellar visitors. It's like searching for a specific type of needle in a haystack made of needles, where the one you're looking for is moving faster than all the others. Meanwhile, the Zwicky Transient Facility at Palomar Observatory in California takes a different approach. This system uses a massive 570 megapixel camera to photograph the northern sky every few nights, looking for anything that appears, disappears, or changes position between observations. The facility's automated systems process billions of individual measurements each night, flagging potential interstellar objects for human review within hours of detection. Dr. Quan-Chi Ye from the University of Maryland, who helped confirm 3I Atlas as an interstellar visitor, explains that speed is crucial in these discoveries. Interstellar objects are often faint and moving rapidly, which means astronomers have only a narrow window to gather detailed observations before they become too distant to study effectively. The faster we can identify and confirm these objects, the more science we can extract from their brief visits. The Catalina Sky Survey in Arizona represents one of the longest-running asteroid detection programs, having discovered more near-Earth objects than any other ground-based survey. Their 3 telescopes cover thousands of square degrees of sky each night, pushing to ever fainter, limiting magnitudes in search of small distant objects. The survey's success comes from its systematic approach, methodically covering the same regions of sky night after night to detect the subtle motions that reveal new visitors. But the real revolution in interstellar object detection is still to come. Later this year, the Vera C. Rubin Observatory in Chile will begin the most comprehensive sky survey in history. With its 8.4-meter mirror and 3.2 gigapixel camera, Rubin will photograph the entire southern sky every few nights for 10 years, creating a movie of the universe that captures everything from distant supernova to nearby asteroids. The implications for interstellar object science are staggering. Current projections suggest that Rubin will detect between 50 and 100 interstellar visitors each year, compared to the handful we've found so far. This 100-fold increase in discovery rate will provide the statistical sample needed to understand whether objects like Oumuamua and 3I Atlas are typical interstellar wanderers or represent something genuinely unusual. Dr. Mario Juric, who leads Rubin's data management efforts, describes the challenge of processing this flood of information. The observatory will generate 20 terabytes of data each night, containing observations of billions of celestial objects. Sophisticated machine learning algorithms will sift through this data stream, identifying potential interstellar objects and alerting astronomers worldwide within 60 seconds of detection. The speed of this alert system could be crucial for studying future interstellar visitors. Unlike the previous discoveries, where weeks or months passed before the object's true nature was recognized, Rubin's rapid alerts will allow astronomers to begin intensive follow-up observations immediately. This could mean the difference between a comprehensive study and a missed opportunity for objects on particularly fast trajectories. European astronomers are contributing their own detection capabilities through the European Space Agency's planned Fly-Eye telescope network. The first telescope is under construction on Mount Mufara in Italy, with additional facilities planned for the southern hemisphere. These wide-field survey telescopes will complement existing detection systems while focusing specifically on potentially hazardous objects that might threaten Earth. The challenge of detecting interstellar objects goes beyond simply having enough telescopes pointed at the sky. These visitors are typically small, dark and moving at extreme velocities that make them difficult to distinguish from instrumental artifacts or cosmic ray hits on detector cameras. Advanced image processing techniques are essential for separating real objects from the noise inherent in sensitive astronomical observations. Machine learning algorithms are increasingly important in this process. Researchers at institutions around the world are training neural networks to recognize the subtle patterns that distinguish interstellar objects from ordinary solar system bodies. These systems can process vast quantities of observational data far faster than human astronomers, flagging potential discoveries for immediate follow-up observations. The citizen science community is also playing an important role in the search for interstellar visitors. The Unistellar network consists of thousands of amateur astronomers worldwide who operate small but sophisticated telescopes from their backyards. Despite their modest size, these instruments have successfully detected 3i Atlas and contributed valuable observations to professional research efforts. Dr. Ariel Grajkowski from the SETI Institute coordinates many of these citizen science efforts, working with amateur astronomers to maximize the scientific return from their observations. The distributed nature of this network provides continuous sky coverage across multiple time zones, ensuring that interesting objects can be monitored around the clock as Earth rotates. But finding interstellar objects is only the beginning of the challenge. Once detected, these visitors must be studied intensively during their brief passage through the inner solar system. This requires coordinating observations across multiple telescopes and wavelengths, from radio waves to gamma rays, to build a complete picture of each object's composition and behavior. The Hubble Space Telescope has provided some of the most detailed images of interstellar visitors, revealing the complex structures of their dust comas and allowing precise measurements of their sizes and rotation states. The James Webb Space Telescope, with its unprecedented infrared sensitivity, can detect heat signatures and molecular emissions that are invisible to ground-based telescopes. Ground-based facilities are also being upgraded specifically for interstellar object studies. The Very Large Telescope in Chile, the Keck telescopes in Hawaii, and the Gemini observatories are all equipped with specialized instruments designed to extract maximum information from faint, rapidly moving targets. These facilities can obtain detailed spectra revealing the chemical compositions of interstellar visitors, providing direct evidence of the conditions that existed in their birth star systems. The coordination required for these intensive observation campaigns is unprecedented in astronomy. When an interstellar object is discovered, observatories around the world must quickly reorganize their schedules to accommodate follow-up observations. Telescope time, normally allocated months or years in advance, must be reallocated on timescales of hours or days. International cooperation is essential for maximizing the scientific return from these rare opportunities. The International Astronomical Union has established protocols for sharing information about newly discovered interstellar objects, ensuring that all qualified research teams have access to the data needed for comprehensive studies. As we've learned more about interstellar visitors, fundamental questions about their nature have become increasingly important. The unusual properties observed in Oumuamua and 3i Atlas have led some researchers to ask whether all interstellar objects are natural formations, or whether some might represent artifacts of technological civilizations. Dr. Avi Loeb from Harvard University has been particularly vocal in suggesting that the anomalous characteristics of some interstellar visitors warrants serious consideration of artificial origins. While this hypothesis remains controversial within the scientific community, it has sparked important discussions about how to distinguish between natural and potentially artificial objects. The debate centers on what observable characteristics might indicate artificial construction: unusual geometric shapes, surface compositions inconsistent with known geological processes, thermal properties suggesting internal heat sources, and trajectories that can't be explained by conventional physics have all been proposed as potential indicators of artificial origin. Most astronomers remain skeptical of the artificial hypothesis, arguing that the unusual properties of interstellar visitors can be explained by natural processes operating under exotic conditions. The chemical compositions and thermal histories of objects formed around different types of stars might indeed produce characteristics unlike anything in our own solar system. But the possibility of artificial interstellar objects has important implications for how we approach future discoveries. If such objects exist, they might represent humanity's first confirmed contact with extraterrestrial intelligence, making their detection and study a matter of profound importance for our species. This uncertainty has led to the development of new analytical frameworks for studying interstellar visitors. Researchers are working to establish clear criteria for distinguishing between natural and potentially artificial objects, based on observable characteristics that can be measured with current technology. The search for interstellar visitors is also driving advances in space-based detection systems. NASA's proposed NEO Surveyor mission will use infrared sensors to detect asteroids and comets from space, potentially providing earlier warning of approaching interstellar objects. The mission's space-based vantage point will eliminate atmospheric interference and allow continuous monitoring of regions of sky that are difficult to observe from the ground. Future missions might go beyond detection to actual interception of interstellar visitors. The European Space Agency's Comet Interceptor mission, currently under development, could potentially be retargeted toward newly discovered interstellar objects. Such missions would require revolutionary propulsion systems and precise navigation capabilities, but they could provide close-up images and direct chemical analysis that would be impossible from ground-based observations. The prospect of sample return missions to interstellar objects represents the ultimate goal of this field. Bringing material from another star system back to Earth for laboratory analysis would provide unprecedented insights into the conditions that exist around alien suns and the processes that form planetary systems throughout the galaxy. Tonight, as observatories around the world begin another night of systematic sky surveying, the next interstellar visitor might already be approaching the edge of our solar system. Somewhere in the data streams flowing from telescopes in Hawaii, Chile, Arizona, and beyond, algorithms are searching for the subtle signs that would herald another messenger from the stars. The detection systems operating tonight represent just the visible surface of a much deeper scientific revolution. Behind every telescope pointing skyward lies a complex web of artificial intelligence systems, machine learning algorithms, and automated analysis programs, working tirelessly to separate genuine cosmic visitors from the billions of false positives generated by instrumental noise, cosmic rays, and ordinary solar system debris. At the University of Washington, Dr. Mario Jurich and his team are developing the software that will power the Rubin Observatory's unprecedented survey capabilities. Their algorithms must process 20 terabytes of data every single night, analyzing the positions and brightnesses of literally billions of celestial objects to identify the handful that might represent genuine interstellar visitors. The computational challenge is staggering. Imagine trying to spot a single changed pixel in a photograph containing billions of pixels, and then determining whether that change represents something genuinely significant or merely instrumental noise. The machine learning systems being deployed for this task represent some of the most sophisticated pattern recognition technology ever applied to astronomical research. Neural networks, trained on millions of observations, learn to recognize the subtle signatures that distinguish interstellar objects from ordinary asteroids and comets. These systems can identify potential discoveries within minutes of observation, automatically triggering follow-up observations at telescopes around the world before human astronomers have even had a chance to review the data. But speed alone isn't enough. The real breakthrough comes from the integration of multiple detection systems working in concert. When the Zwicky Transient Facility in California identifies a potentially interesting moving object, automated systems immediately cross-reference that detection with observations from Atlas telescopes in Hawaii and Chile, the Catalina Sky Survey in Arizona, and soon the Rubin Observatory. This multi-telescope verification happens in real time, providing confirmation of genuine discoveries while filtering out the countless false alarms that plague individual detection systems. The sophistication of these networks becomes apparent when you consider the scale of the challenge they face. Every night, ground-based surveys detect thousands of moving objects. The vast majority are ordinary asteroids following predictable orbits around the Sun. A smaller number are comets, their distinctive tails making them relatively easy to classify. But hidden among these routine discoveries might be the next interstellar visitor, distinguished only by subtle orbital characteristics that require precise measurements over multiple nights to confirm. Dr. Robert Werrick at the University of Western Ontario, who discovered both Oumuamua and helped confirm 3I Atlas, describes the painstaking process of verification that follows each potential discovery. Initial observations might suggest an unusual trajectory, but confirming interstellar origin requires tracking an object across multiple nights to precisely measure its orbit. During this crucial verification period, the object is often fading as it moves away from Earth, creating a race against time to gather enough observations for definitive classification. The international coordination required for this verification process operates on a scale that would have been impossible just a decade ago. Within hours of a potential discovery, observatories across multiple continents receive automated alerts containing precise coordinates and suggested observation strategies. The Minor Planet Center in Massachusetts serves as the central clearinghouse for these observations, collecting data from dozens of facilities worldwide and maintaining the official database of confirmed interstellar objects. This global network faces constant pressure to improve its capabilities as the rate of potential discoveries accelerates. The Rubin Observatory alone will generate more candidate detections in a single night than the entire astronomical community currently processes in a month. Handling this flood of information will require not just faster computers, but entirely new approaches to data analysis and scientific collaboration. European researchers are contributing their own innovations to this challenge through the development of distributed computing networks that can process observational data in real time. The European Southern Observatory operates a dedicated facility for rapid analysis of transient astronomical events, using cloud computing resources to analyze observations from telescopes across 3 continents simultaneously. These technological advances are enabling entirely new approaches to interstellar object science. Rather than simply waiting for objects to be discovered and then scrambling to study them during their brief visibility, astronomers are developing predictive systems that can identify likely interstellar visitors weeks or months before their closest approach to the Sun. This advance warning would allow for much more comprehensive observation campaigns, potentially including space-based missions to intercept and study these cosmic messengers up close. The European Space Agency's Comet Interceptor mission represents the most ambitious attempt yet to study an interstellar visitor directly. Originally designed to rendezvous with a long-period comet from the outer reaches of our solar system, the mission could potentially be retargeted toward a newly discovered interstellar object. The spacecraft would deploy multiple probes to study the visitor from various angles, providing detailed measurements of its composition, structure, and behavior that would be impossible to obtain from ground-based observations. But such missions face enormous technical challenges. Interstellar objects travel at velocities that make conventional spacecraft rendezvous techniques impossible. Instead of the gentle orbital insertions used for missions to planets and asteroids, intercepting an interstellar visitor would require precise trajectory calculations and split-second timing to achieve even a brief flyby. The spacecraft would have only minutes or hours to complete its entire scientific program before the target vanished back into interstellar space. NASA's Jet Propulsion Laboratory is studying even more ambitious concepts for future interstellar visitor missions. Their preliminary designs include nuclear-powered spacecraft that could match velocities with fast-moving targets, enabling extended observation periods rather than brief flybys. Such missions would require revolutionary advances in propulsion technology, but they could provide the detailed characterization needed to definitively determine whether interstellar visitors represent natural phenomena or something more exotic. The question of what constitutes evidence for artificial origin remains one of the most contentious issues in contemporary astronomy. Dr. Abraham Loeb's hypothesis that Oumuamua might represent alien technology sparked intense debate within the scientific community, with researchers divided between those who see intriguing anomalies worth investigating and those who argue that natural explanations can account for all observed phenomena. The debate has led to the development of more rigorous frameworks for evaluating potentially artificial objects. Dr. Jason Wright at Penn State University has proposed specific observational criteria that could distinguish between natural and artificial interstellar visitors. These include geometric shapes optimized for specific functions rather than natural formation processes, surface compositions inconsistent with known geological or chemical processes, and most importantly, behavior patterns that cannot be explained by conventional gravitational and thermodynamic forces. Applying these criteria to future discoveries will require unprecedented precision in observational measurements. Determining whether an object's shape represents natural formation or artificial design demands detailed imaging that pushes current telescope capabilities to their limits. Chemical composition analysis requires spectroscopic observations sensitive enough to detect trace elements and molecular species in extremely faint, rapidly moving targets. The Hubble Space Telescope has already demonstrated some of these capabilities in its observations of 3I Atlas, revealing the complex morphology of the object's dust coma and allowing precise estimates of its nuclear size and rotation state. But future discoveries will require even more sophisticated space-based observations, potentially including coordinated campaigns involving multiple telescopes working together to build comprehensive portraits of interstellar visitors. The James Webb Space Telescope represents a quantum leap in these capabilities, with infrared sensitivity that can detect thermal emissions from interstellar objects and spectroscopic capabilities that can identify molecular species invisible to optical telescopes. Webb's observations of future interstellar visitors could provide the chemical fingerprints needed to determine their origins and formation histories with unprecedented precision. Ground-based facilities are also being upgraded specifically for interstellar object studies. The extremely large telescope, currently under construction in Chile, will have a primary mirror more than 3 times larger than any existing optical telescope, providing the light-gathering power needed to obtain detailed spectra of even the faintest interstellar visitors. Its advanced adaptive optics systems will deliver image quality approaching that of space-based telescopes, enabling morphological studies that could reveal artificial structures if they exist. The integration of these observational capabilities with sophisticated theoretical models is creating new possibilities for understanding interstellar visitors. Computer simulations can now model the formation and evolution of small bodies around different types of stars, predicting the chemical compositions and physical properties that natural interstellar objects should exhibit. Comparing these predictions with actual observations provides a powerful test for distinguishing between natural and potentially artificial phenomena. Dr. Alan Stern, principal investigator of NASA's New Horizons mission to Pluto, has emphasized the importance of maintaining scientific rigor while remaining open to extraordinary possibilities. The history of astronomy is filled with phenomena that initially seemed impossible or artificial before being explained by advances in theoretical understanding. But that same history also demonstrates the value of careful observation and analysis in revealing genuinely new aspects of the natural world. The citizen science community continues to play an increasingly important role in these efforts. The Unistellar network now includes thousands of amateur astronomers operating sophisticated telescopes from locations around the world. These distributed observations provide continuous monitoring capabilities that complement professional facilities, ensuring that interesting objects can be tracked around the clock as Earth rotates. Dr. Frank Marcus from the SETI Institute coordinates many of these citizen science efforts, developing software tools that allow amateur astronomers to contribute meaningful observations to professional research programs. The network has already demonstrated its capabilities by successfully detecting and tracking 3i Atlas, despite the object's extreme faintness, proving that distributed networks of small telescopes can complement large professional facilities in studying interstellar visitors. The data analysis techniques developed for interstellar object research are also finding applications in other areas of astronomy. Machine learning algorithms trained to identify unusual moving objects are being adapted for studies of asteroids, comets, and even distant galaxies. The real-time data processing systems developed for rapid interstellar object confirmation are being deployed for studies of supernovae, gamma-ray bursts, and other transient astronomical phenomena. These technological spillovers highlight the broader scientific value of interstellar visitor research, regardless of whether such objects ultimately prove to be natural or artificial. The challenge of detecting and studying these rare, fast-moving visitors is driving innovations in observational astronomy, data analysis, and international scientific collaboration that will benefit many other areas of research. As detection capabilities continue to improve, astronomers are preparing for the possibility that interstellar visitors might be more common than current observations suggest. The 3 confirmed interstellar objects discovered so far might represent only the largest and most active members of a much larger population of smaller, less conspicuous visitors that have passed through our solar system undetected. Statistical models based on the discovery rate of known interstellar objects suggest that dozens or hundreds of such visitors might pass through the inner solar system each year. Most would be too small or inactive to detect with current surveys, but the next generation of facilities like the Rubin Observatory will have the sensitivity to find much fainter objects, potentially revealing the true scope of interstellar traffic through our cosmic neighbourhood. The implications of discovering a large population of interstellar visitors extend far beyond astronomy. These objects represent samples of material from planetary systems throughout our galaxy, carrying information about the chemical compositions, formation processes, and perhaps even biological signatures of worlds orbiting distant stars. Studying them provides a direct way to investigate the diversity of planetary system formation without waiting for the technological advances needed for interstellar space missions. The possibility that some interstellar visitors might be artificial adds another dimension to these considerations. If technological civilizations exist elsewhere in the galaxy, they might use interstellar probes to explore nearby star systems, much as we plan to study other stars with future space missions. Detecting and studying such probes could provide our first direct evidence of extraterrestrial intelligence and insight into the technologies and intentions of alien civilizations. But even if all interstellar visitors prove to be natural phenomena, their study is revealing fundamental aspects of how planetary systems form and evolve throughout the galaxy. The unusual chemical compositions observed in some interstellar objects suggest that the processes operating in other stellar systems can produce materials and structures unlike anything found in our own solar system. Tonight, as automated systems continue their patient vigil across observatories worldwide, the next chapter in this story might already be unfolding. Somewhere in the vast data streams flowing from telescopes in Chile, Hawaii, California, and beyond, algorithms are analysing billions of measurements, searching for the subtle patterns that would herald another visitor from the stars. The discovery might come tomorrow, next week, or next year, but when it happens, the global network of detection systems and analysis programs will be ready to spring into action, coordinating observations across continents to capture every possible detail of our latest cosmic messenger. The mathematics behind these detection systems reveal just how remarkable our current capabilities have become. Consider the precision required to identify a single moving object among the billions of stars captured in each night's observations. The Zwicky Transient Facility alone processes measurements of approximately 400 million celestial objects every night, comparing their positions and brightness levels to previous observations with accuracy measured in thousandths of an arc second. Dr. Matthew Graham, who oversees the facility's data processing operations, describes the computational challenge in almost poetic terms. We're essentially creating a digital memory of the entire northern sky, he explains, updating that memory every few nights and flagging anything that has changed position by even the tiniest amount. The algorithms must distinguish between genuine object motion and the countless sources of measurement uncertainty that plague astronomical observations, from atmospheric turbulence to subtle variations in detector sensitivity. This level of precision becomes even more impressive when you consider the speeds involved. Interstellar visitors can cross several arc minutes of sky in a single night, distances that seem tiny until you realize they represent millions of miles of actual motion through space. Tracking these objects requires coordinating observations across multiple telescopes with timing precise enough to account for light travel times between different observational sites on Earth. The challenge becomes particularly acute for objects discovered near the edge of our detection capabilities. Faint interstellar visitors might be visible for only a few nights before they fade below the sensitivity thresholds of even our largest telescopes. During this brief window, astronomers must gather enough observations to precisely determine the object's orbit, confirm its interstellar origin, and begin the intensive studies needed to characterize its composition and behavior. Dr. Davide Farnocchia from NASA's Jet Propulsion Laboratory specializes in the orbital dynamics of small solar system bodies, including the complex calculations required to distinguish between bound and unbound trajectories. The mathematical precision required for these determinations pushes the limits of current computational capabilities, particularly when dealing with objects observed over very short time spans with limited positional accuracy. Recent advances in orbit determination software are making these calculations more reliable and faster. Machine learning techniques can now identify likely interstellar candidates within hours of initial detection, rather than the days or weeks traditionally required for manual analysis. This acceleration in identification timelines is crucial for maximizing the scientific return from each discovery, allowing researchers to begin intensive follow-up observations while objects are still relatively bright and accessible to detailed study. The international nature of modern astronomical collaboration becomes particularly evident in the rapid response protocols developed for interstellar object discoveries. Within minutes of a confirmed detection, automated systems distribute alerts to observatories across multiple continents, providing precise coordinates and recommended observation strategies tailored to each facility's capabilities. Dr. Alan Harris from the German Aerospace Centre coordinates many of these international efforts through the European Space Agency's Space Situational Awareness Programme. The goal is to ensure continuous monitoring coverage as Earth rotates, preventing gaps in observations that could result in losing track of rapidly moving targets. This requires careful coordination across different time zones, weather patterns, and telescope availability schedules. The sophistication of these coordination efforts extends to the automated scheduling systems now being deployed at major observatories. When an interstellar object alert is received, these systems can automatically evaluate observation priorities, reschedule routine programs, and optimize telescope pointing sequences to maximize data collection efficiency. The entire process, from initial detection to coordinated global follow-up, can now occur with minimal human intervention. But perhaps the most significant development in interstellar object detection is the emergence of specialized space-based observation platforms. NASA's NEOWISE mission, originally designed to survey asteroids and comets in infrared wavelengths, has proven unexpectedly effective at detecting and characterizing interstellar visitors. The space-based vantage point eliminates atmospheric interference while providing access to infrared wavelengths that reveal thermal properties invisible to ground-based telescopes. The infrared observations from NEOWISE have provided crucial insights into the thermal behavior of interstellar objects, revealing details about their surface compositions and internal heat distribution that complement visible light studies. Dr. Amy Mainzer, who leads the NEOWISE science team, describes how infrared observations can distinguish between different types of surface materials and detect subtle temperature variations that might indicate unusual composition or structure. Future space missions will expand these capabilities dramatically. The proposed NEO Surveyor mission will deploy a dedicated infrared telescope specifically designed to detect and track small moving objects throughout the solar system. With sensitivity improvements of several orders of magnitude over current space-based systems, NEO Surveyor could potentially detect interstellar visitors while they're still in the outer solar system, providing months of advance warning rather than the weeks currently available. This extended observation timeline would revolutionize interstellar object science by allowing comprehensive observation campaigns to be planned and coordinated before objects reach peak brightness. Rather than the current scramble to gather data during brief visibility windows, astronomers could conduct systematic studies, tracking objects from initial detection through closest approach and back out to the detection limits. The European Space Agency is developing complementary capabilities through their proposed HERA mission architecture. While primarily focused on asteroid deflection demonstration, the mission includes advanced navigation and imaging systems that could be rapidly reconfigured for interstellar object intercept missions. The technologies being developed for precision asteroid operations translate directly to the challenges of studying fast-moving interstellar visitors. Dr. Ian Carnelli, who manages ESA's planetary defense activities, emphasizes the dual-use nature of these technological developments. The same precision guidance systems needed to deploy impactor spacecraft against potentially hazardous asteroids can be adapted for scientific missions to study interstellar objects. The rapid response capabilities required for planetary defense scenarios provide exactly the kind of quick reaction mission architecture needed to intercept unexpected cosmic visitors. These mission concepts are driving advances in autonomous spacecraft operations that could prove crucial for interstellar object studies. Traditional spacecraft missions rely on detailed pre-planning and ground-based control for major operations, but the brief encounter times and limited communication windows associated with interstellar visitors require much more autonomous capability. Artificial intelligence systems are being developed that can make real-time decisions about observation priorities, instrument configurations, and trajectory corrections without waiting for commands from Earth. These systems must balance competing scientific objectives while adapting to unexpected discoveries or equipment failures during critical observation periods. The challenge of autonomous operations becomes particularly complex when considering multi-spacecraft missions to interstellar visitors. Coordinating multiple probes during high-speed flybys requires split-second timing and the ability to adapt observation strategies based on discoveries made by lead spacecraft. The communication delays inherent in deep space operations make ground-based control impossible for these time-critical operations. Laboratory simulations of these scenarios are pushing the boundaries of artificial intelligence and robotics research. NASA's Jet Propulsion Laboratory operates dedicated facilities where spacecraft AI systems are tested under realistic mission conditions, including the communication delays, limited power budgets, and equipment constraints that would characterize actual interstellar visitor encounters. These technological developments are occurring alongside advances in ground-based observation capabilities that promise to dramatically improve our ability to study interstellar objects from Earth. The extremely large telescope, currently under construction in Chile, will provide light-gathering power more than 10 times greater than any existing optical facility. Dr. Roberto Gilmozzi, who oversees the telescope's scientific planning, describes capabilities that seem almost science-fictional. The facility will be able to obtain detailed spectra of objects millions of times fainter than what the human eye can see, revealing chemical compositions and physical properties with precision previously thought impossible. For interstellar visitors, this means the ability to detect and analyze trace constituents that could provide definitive evidence of their origins and formation histories. The telescope's advanced adaptive optics systems will deliver image quality approaching theoretical limits, enabling morphological studies that could reveal structural details invisible to current instruments. If artificial interstellar objects exist, these observations might provide the first definitive evidence of non-natural construction through direct imaging of geometric features inconsistent with natural formation processes. But the most transformative aspect of next-generation ground-based facilities may be their ability to conduct real-time spectroscopic monitoring of interstellar visitors. Rather than obtaining single snapshots of object properties, future observations could track chemical and physical changes occurring as visitors respond to solar heating or other environmental factors. Dr. Euwijn van Dishoeck from Leiden University, who specializes in interstellar chemistry, explains how continuous spectroscopic monitoring could reveal dynamic processes occurring within interstellar objects. The sublimation of different ice species, the evolution of dust grain properties and potential outgassing events could all be tracked in real time, providing unprecedented insights into the internal structure and composition of these cosmic messengers. Such observations might also detect signatures of biological activity if interstellar objects serve as vehicles for panspermia, the transfer of life between star systems. While most scientists remain skeptical about the survival of biological systems during million-year interstellar journeys, the possibility cannot be entirely dismissed without careful observation of the organic chemistry occurring within interstellar visitors. The search for biological signatures in interstellar objects is driving development of increasingly sensitive detection methods. New spectroscopic techniques can identify complex organic molecules at extremely low concentrations, while advanced imaging systems can detect microscopic structures that might indicate biological origin. Dr. Christopher McKay from NASA's Ames Research Center, a pioneer in astrobiology research, emphasizes the importance of maintaining rigorous scientific standards while remaining open to extraordinary discoveries. The detection of life signatures in interstellar objects would represent one of the most significant discoveries in human history, requiring exceptional evidence and careful verification before acceptance by the scientific community. The protocols being developed for such discoveries draw lessons from previous controversies in astrobiology, including claims of Martian life in meteorites and disputed evidence for extramophil organisms in terrestrial environments. Multiple independent confirmation, rigorous contamination control, and comprehensive peer review would all be essential elements of any claim for biological signatures in interstellar material. These considerations become particularly important when considering sample return missions to interstellar objects. Bringing material from another star system back to Earth for laboratory analysis offers the possibility of definitive characterization using the full range of terrestrial analytical techniques, but also raises unprecedented challenges for planetary protection. Current planetary protection protocols focus on preventing contamination between Earth and other bodies within our solar system, but interstellar material presents entirely new categories of risk. The biological, chemical, and even physical properties of matter formed around alien stars remain completely unknown, making risk assessment extraordinarily difficult. Dr. Catherine Conley, who previously served as NASA's Planetary Protection Officer, has begun developing preliminary frameworks for handling interstellar samples. The protocols would likely require containment facilities more sophisticated than any currently existing, with multiple redundant barriers against the release of potentially hazardous material into Earth's environment. The scientific value of such samples would be immense, potentially providing definitive answers to fundamental questions about the formation and evolution of planetary systems throughout the galaxy. Laboratory analysis could reveal isotopic signatures that would pinpoint the stellar environment where interstellar objects formed, chemical compositions that would indicate the presence or absence of biological processes, and structural details that might distinguish between natural and artificial construction. But the technical challenges of obtaining such samples remain formidable. Current spacecraft propulsion systems cannot match the velocities of interstellar visitors, limiting encounters to brief high-speed flybys that provide little opportunity for sample collection. Revolutionary advances in propulsion technology would be required to enable the extended rendezvous missions needed for comprehensive sample return operations. Nuclear propulsion systems offer one potential solution, providing the high specific impulse needed to match velocities with fast-moving targets. NASA's ongoing development of nuclear thermal and nuclear electric propulsion could eventually enable spacecraft to achieve the delta-V requirements for interstellar object intercept missions, though such capabilities remain years or decades away from operational deployment. Solar sail technology represents another promising approach, using radiation pressure from sunlight to achieve very high velocities without the mass penalties associated with conventional propulsion systems. Recent demonstrations of solar sail spacecraft have validated the basic technology, though scaling up to the performance levels needed for interstellar visitor missions presents significant engineering challenges. The Japan Aerospace Exploration Agency's successful Ikaros solar sail mission demonstrated controlled flight using radiation pressure alone, while NASA's Near-Earth Asteroid Scout mission will provide additional validation of solar sail technology for small body exploration. These proof-of-concept missions are paving the way for more ambitious applications, including potential interstellar visitor intercept capabilities. Dr. Les Johnson, who manages NASA's solar sail technology development, describes mission concepts that could achieve intercept velocities approaching those of typical interstellar visitors. Such missions would require sails kilometers in diameter, deployed with unprecedented precision, but the basic physics appears sound, and the required materials are within reach of current technology. Even more exotic propulsion concepts are being investigated for future interstellar visitor missions. Breakthrough, Starshot's an ambitious privately funded project, aims to develop laser-propelled light sails capable of reaching 20% of light speed for interstellar missions. While this technology is intended primarily for missions to nearby star systems, scaled-down versions might enable rapid intercept missions within our own solar system. The technological developments driven by interstellar visitor research are also contributing to broader advances in space exploration and planetary science. High-precision navigation systems, autonomous spacecraft operations, and rapid response mission architectures all have applications to traditional planetary missions, asteroid studies, and outer solar system exploration. The data analysis techniques developed for identifying interstellar objects, among billions of routine observations, are finding applications in other areas of astronomy, from the search for potentially hazardous asteroids to studies of variable stars and transient phenomena. Machine learning algorithms trained on interstellar object detection are being adapted for identifying supernova, gravitational wave counterparts, and other time-critical astronomical events. The international collaboration frameworks established for interstellar object research are serving as models for other large-scale scientific projects. The protocols for rapid data sharing, coordinated observation campaigns, and real-time analysis are being adopted by research programs studying everything from gamma-ray bursts to exoplanet transits. But perhaps the most significant impact of interstellar visitor research lies in its philosophical implications for humanity's place in the cosmos. Each new discovery reinforces our growing understanding that our solar system is not an isolated island in space, but rather a way station in vast networks of matter and energy that connect star systems throughout the galaxy. The realization that material regularly flows between stellar systems challenges traditional boundaries in planetary science and asked cause of distant stars' robiology. Chemical elements synthesized in the organic molecules formed in alien environments, and possibly even biological systems adapted to interstellar travel, might all be represented among the objects currently approaching our solar system. This perspective transforms our understanding of planetary evolution and the potential for life throughout the universe. Rather than viewing each star system as an independent laboratory for chemical evolution, we must consider the possibility that interstellar exchange processes create connections and influences that span vast regions of the galaxy. The implications extend to our own origins and future as well. The chemical elements in our bodies were forged in stellar cores and distributed through space by supernova explosions. But interstellar objects might represent more direct connections to other worlds. The carbon in our DNA, the oxygen in our atmosphere, and the water in our oceans might have journeyed between star systems multiple times before contributing to the formation of Earth. Looking toward the future, humanity's own expansion into space might follow similar patterns. Our spacecraft exploring the outer solar system will eventually escape the sun's gravitational influence, becoming artificial interstellar objects carrying technological signatures of our civilization to other star systems. Future civilizations might study these artifacts, much as we now analyze natural interstellar visitors, seeking clues about the biological and technological evolution that occurred around our sun. The search for the next interstellar visitor continues tonight, as automated systems maintain their patient watch across observatories worldwide. Somewhere in the darkness beyond Neptune's orbit, another messenger from the stars might already be approaching, carrying within its ancient structure new mysteries for humanity to unravel. The global network of telescopes, computers, and dedicated researchers stands ready to detect, track, and study whatever cosmic visitor appears next in our small corner of the galaxy. In underground control rooms, from Hawaii to Chile to South Africa, night shift operators monitor streams of data flowing from robotic telescopes that never sleep, never blink, and never lose focus in their systematic scan of the cosmos. Each image captured tonight will be compared with previous observations, analysed by sophisticated algorithms, and searched for the subtle signs of movement that would herald another visitor from beyond our solar system. The next discovery might happen tomorrow, next month, or next year, but when it comes, the response will be immediate and global. Alert systems will notify observatories across 6 continents within minutes, triggering coordinated observation campaigns designed to capture every possible detail of our latest cosmic guest. Telescopes will swing toward new coordinates, spectrographs will begin analysing the chemical composition of material from another star, and researchers around the world will begin the careful work of determining what this new visitor might teach us about the universe beyond our solar system. The data analysis centres that process these nightly observations operate with a precision that borders on the supernatural. At the University of Arizona's Spacewatch facility, computers sift through thousands of images every night, each one containing millions of individual points of light. The challenge isn't just finding moving objects among this stellar multitude, but distinguishing between the predictable motions of ordinary asteroids and the hyperbolic trajectories that betray visitors from other stars. Dr. Eric Christensen, who leads the Catalina Sky Survey, describes the moment of discovery with quiet reverence. When you first spot something moving unusually fast, he explains, there's always this flutter of excitement mixed with skepticism. Most of the time, it turns out to be measurement error or an ordinary object seen at an unusual angle. But occasionally, very occasionally, the measurements hold up under scrutiny, and you realise you're looking at something that doesn't belong to our solar system. The verification process that follows such discoveries unfolds with methodical precision across multiple continents. Within hours of identifying a potential interstellar visitor, automated systems dispatch alerts to observatories worldwide, each facility contributing its own measurements to build an increasingly accurate picture of the object's trajectory. The Minor Planets Center in Massachusetts serves as the central hub for this global effort, collecting observations from dozens of telescopes and performing the complex orbital calculations needed to distinguish between solar system natives and genuine interstellar travelers. This international coordination operates on timescales that would have been impossible just a decade ago. When Oumuamua was discovered in 2017, it took weeks to confirm its interstellar nature. By the time 3i Atlas appeared in 2025, that confirmation timeline had compressed to mere days, thanks to improved detection algorithms and more efficient data-sharing protocols. The European Southern Observatory's contribution to this global network demonstrates the sophisticated technology now deployed in the search for interstellar visitors. Their survey telescopes in Chile operate with sensitivity levels that can detect objects millions of times fainter than what the human eye can perceive, while advanced image processing systems automatically flag anything that moves against the background stars. Dr. Marco Micheli, who specialises in small body dynamics at the European Space Agency, emphasises how the challenge extends beyond simple detection. Once you've found something moving unusually fast, he notes, you need to determine not just where it's going, but where it came from. Tracing an object's path backward through millions of years of galactic motion requires accounting for gravitational influences from countless stars, each of which has moved through space during the object's long journey. These trajectory analyses are revealing surprising patterns in how interstellar objects enter our solar system. Rather than arriving from random directions, as purely chance encounters might suggest, some visitors, like 3i Atlas, approach along paths that seem almost deliberately chosen to maximize their visibility from Earth. This apparent bias likely reflects observational selection effects rather than intentional targeting, but it highlights how much we still don't understand about the population of objects drifting between the stars. The physical characterization of interstellar visitors presents its own set of challenges that push current observational technology to its limits. When these objects are discovered, they're typically millions of miles away and moving at speeds that make detailed study extraordinarily difficult. Ground-based telescopes must track targets that cross significant portions of the sky each night, while space-based observatories struggle with the precise pointing requirements needed to keep faint, rapidly moving objects centered in their fields of view. NASA's Hubble Space Telescope has provided some of the most detailed observations of interstellar visitors, but even this premier facility can study such objects for only brief periods before they fade beyond detection limits. The telescope's observations of 3I Atlas revealed intricate details of the object's dust coma and allowed precise measurements of its rotation state, but each observation required careful scheduling and coordination to account for the object's rapid motion across the sky. The spectroscopic analysis of interstellar visitors offers tantalizing glimpses into the chemistry of alien worlds, but interpreting these observations requires pushing theoretical models into entirely new territory. Dr. Bin Yang from the European Southern Observatory has spent years developing techniques for extracting chemical information from the faint light reflected by these distant objects. The challenge lies not just in detecting specific molecules, but in understanding how materials formed around different types of stars might behave under the extreme conditions of interstellar space. Recent observations have revealed chemical compositions that challenge our understanding of how planetary systems form and evolve. Some interstellar visitors show evidence of water ice, suggesting formation in cold outer regions similar to our own Kuiper belt. Others display unusual ratios of carbon compounds that might indicate formation around stars with very different chemical compositions than our Sun. The thermal properties of interstellar objects provide additional clues about their origins and internal structure. Infrared observations from NASA's Spitzer Space Telescope and other facilities reveal how these visitors respond to solar heating as they pass through the inner solar system. Some objects warm and cool in ways consistent with conventional rocky or icy compositions, while others display thermal behaviors that suggest more exotic internal structures. Dr. Michael Kelly from the University of Maryland analyzes these thermal signatures to understand the internal composition of interstellar visitors. The way an object heats up and cools down tells us about its density, thermal conductivity, and internal structure, he explains. Some of the measurements we've obtained don't match any materials we're familiar with from our own solar system, which could indicate either unusual formation conditions or possibly artificial construction. The artificial hypothesis continues to generate intense debate within the astronomical community, with researchers divided between those who see intriguing anomalies worth investigating and those who argue that natural processes can explain all observed phenomena. The controversy centers on establishing clear criteria for what would constitute definitive evidence of artificial origin versus natural formation under exotic conditions. Dr. Abraham Loeb from Harvard University maintains that the unusual characteristics of some interstellar visitors warrant serious consideration of technological origins. The combination of anomalous trajectories, unusual shapes, and unexpected thermal properties could potentially indicate artificial construction, though he acknowledges that extraordinary claims require extraordinary evidence. The scientific mainstream remains largely skeptical of artificial explanations, pointing out that interstellar objects represent our first detailed observations of materials formed around other stars. The unusual properties that seem anomalous might simply reflect our limited understanding of planetary formation processes operating under very different conditions than those found in our own solar system. Dr. Alan Harris from the German Aerospace Centre emphasises the importance of maintaining rigorous scientific standards while investigating these possibilities. We need to be extremely careful about distinguishing between what we observe and what we infer, he notes. Unusual doesn't necessarily mean artificial, and we have to exhaust all natural explanations before considering more exotic possibilities. The development of objective criteria for evaluating potentially artificial objects is driving advances in both observational techniques and theoretical modelling. Researchers are working to establish quantitative measures that could distinguish between natural formation processes and possible technological construction based on observable characteristics like geometric regularity, surface composition, and thermal behaviour. Future space missions offer the possibility of resolving these questions through direct investigation of interstellar visitors. The European Space Agency's Comet Interceptor mission, currently in development, could potentially be retargeted toward newly discovered interstellar objects, providing close-up observations that would be impossible from ground-based telescopes. Such missions face extraordinary technical challenges due to the extreme velocities involved in interstellar visitor encounters. Conventional spacecraft rendezvous techniques that work for asteroids and comets within our solar system become impossible when dealing with objects moving at 30 to 50 kilometers per second relative to the Sun. Dr. Colin McInnes from the University of Glasgow studies advanced propulsion concepts that might enable future interstellar visitor intercept missions. Solar sails using radiation pressure from sunlight could potentially achieve the high velocities needed for intercept trajectories, while nuclear propulsion systems might provide the specific impulse required for extended rendezvous operations. The technological requirements for such missions are driving innovations that could benefit many areas of space exploration. Autonomous navigation systems capable of making real-time decisions during high-speed encounters, advanced imaging systems that can function while moving at extreme velocities, and miniaturized scientific instruments that can gather comprehensive data during brief flyby opportunities all represent developments with applications far beyond interstellar visitor studies. Laboratory simulations of interstellar visitor encounters are helping engineers understand the challenges that future missions would face. NASA's Jet Propulsion Laboratory operates specialized facilities where spacecraft systems are tested under conditions that simulate the communication delays, power constraints, and operational timelines that would characterize actual intercept missions. The artificial intelligence systems being developed for these missions must make complex decisions about observation priorities and instrument operations without real-time input from ground controllers. The brief encounter times and vast distances involved make traditional spacecraft operations impossible, requiring unprecedented levels of autonomous capability. Dr. Steve Chien, who leads JPL's artificial intelligence research, describes systems that can adapt observation strategies based on discoveries made during the encounter itself. If initial measurements reveal unexpected characteristics, the AI must rapidly reconfigure instruments and modify observation sequences to maximize scientific return from the limited contact time. These autonomous systems are being trained using machine learning techniques that allow them to recognize and respond to novel situations that weren't anticipated during mission planning. The challenge lies in developing AI systems robust enough to handle genuinely unprecedented discoveries while maintaining the reliability required for expensive space missions. The ground-based detection systems that will identify future interstellar visitors are also benefiting from advances in artificial intelligence and machine learning, the Vera-C, Rubin Observatory's legacy. Survey of space and time will generate unprecedented volumes of astronomical data, requiring automated analysis systems that can identify potential interstellar objects among billions of routine observations. Dr. Jelko Ivezic from the University of Washington leads the development of these analysis systems, which must distinguish between genuine interstellar visitors and the countless false positives generated by instrumental artifacts, cosmic ray hits, and measurement uncertainties. The machine learning algorithms being developed for this task represent some of the most sophisticated pattern recognition systems ever applied to astronomical research. The real-time processing requirements for these systems push the boundaries of current computing technology. Every night, the Rubin Observatory will capture 20 terabytes of data containing measurements of billions of celestial objects. Potential interstellar objects must be identified and verified within hours of observation to enable prompt follow-up by other facilities before the objects fade beyond detection limits. The distributed computing networks being developed to handle this data processing challenge operate across multiple continents, using cloud computing resources to analyze observations in real time. The European Southern Observatory coordinates similar networks that can process data from telescopes worldwide, ensuring that potential discoveries are identified and verified as quickly as possible. The international nature of modern interstellar visitor research reflects the global significance of these discoveries. No single nation or institution possesses all the resources needed to detect and study these rare cosmic messengers effectively. Success requires unprecedented cooperation between observatories, space agencies, and research institutions worldwide. Dr. Gerhard Drollshagen from the European Space Agency's Space Situational Awareness Programme coordinates many of these international efforts, ensuring that observation capabilities are distributed globally to provide continuous coverage as Earth rotates. The goal is to prevent gaps in monitoring that could result in losing track of rapidly moving targets during critical observation periods. The protocols developed for international cooperation in interstellar visitor research are serving as models for other time-critical astronomical phenomena. The same coordination mechanisms used for studying cosmic messengers from other star systems are being adapted for research on supernova, gamma-ray bursts, and gravitational wave counterparts. The educational impact of interstellar visitor research extends far beyond the professional astronomical community. Universities worldwide are incorporating these discoveries into curricula that help students understand how scientific knowledge develops through careful observation and analysis over time. Michelle Bannister from the University of Canterbury describes how interstellar visitor discoveries provide perfect case studies in scientific methodology. Students can follow the entire process, from initial detection through confirmation and detailed characterization, learning firsthand how astronomers distinguish between different hypotheses based on observational evidence. The public fascination with interstellar visitors has also created unprecedented opportunities for science communication and outreach. Planetariums worldwide have developed programs that allow visitors to explore the implications of these discoveries, while online platforms enable amateur astronomers to contribute to professional research efforts. The citizen science networks that emerge during the study of recent interstellar visitors demonstrate the potential for broader public participation in cutting-edge astronomical research. Thousands of amateur astronomers worldwide now operate sophisticated telescopes that can contribute meaningful observations to professional studies, creating a distributed network of observers that complements major observatory facilities. Dr. Frank Markis from the SETI Institute coordinates many of these citizen science efforts, developing software tools that allow amateur observers to contribute high-quality data to professional research programs. The network has already demonstrated its capabilities by successfully tracking faint interstellar visitors that challenge even large professional telescopes. The technological advances driven by interstellar visitor research are creating new possibilities for amateur astronomical observations. Small telescopes equipped with sensitive CCD cameras and automated tracking systems can now detect and monitor objects that were beyond the reach of professional facilities just a few decades ago. These distributed observation networks provide capabilities that complement rather than compete with major observatory facilities. While professional telescopes excel at detailed spectroscopic analysis and precise photometry, amateur networks offer continuous monitoring capabilities across multiple time zones and weather patterns. The data analysis techniques developed for processing observations from these distributed networks are finding applications in other areas of astronomy and space science. Machine learning systems that can combine observations from telescopes with different characteristics and calibration standards are being adapted for studies of variable stars, exoplanet transits, and solar system dynamics. The philosophical implications of interstellar visitor discoveries continue to resonate throughout the scientific community and broader society. Each new detection reinforces our understanding that our solar system exists within a dynamic galactic environment where material regularly flows between star systems over vast timescales. This perspective challenges traditional boundaries between planetary science, stellar astronomy, and astrobiology. The possibility that organic molecules or even biological systems might travel between star systems aboard interstellar objects suggests connections between worlds that span incredible distances and time periods. Christopher McKay from NASA's Ames Research Center studies the potential for biological material to survive the extreme conditions of interstellar space. While most scientists remain skeptical about the possibility of living organisms surviving million-year journeys between stars, the question cannot be answered definitively without careful analysis of interstellar visitor compositions. The detection techniques being developed for identifying biological signatures in interstellar objects push the boundaries of current analytical chemistry. New spectroscopic methods can identify complex organic molecules at extremely low concentrations, while advanced imaging systems can detect microscopic structures that might indicate biological origins. The protocols being developed for handling potentially biological material from interstellar objects draw on lessons learned from Mars sample return planning and terrestrial contamination control procedures. Multiple layers of containment and analysis would be required to ensure both scientific validity and planetary protection in the event that interstellar material contained active biological systems. The possibility of detecting technological signatures in interstellar objects presents even greater challenges for scientific verification and interpretation. Clear criteria must be established for distinguishing between natural phenomena and possible artificial construction, based on observable characteristics that can be measured with current instrumentation. Dr. Jason Wright from Penn State University studies potential technological signatures that might be detectable in astronomical observations. The challenge lies in identifying characteristics that could not plausibly result from natural processes, while accounting for the vast range of conditions that might exist in planetary systems throughout the galaxy. The search for technological signatures in interstellar objects is driving development of increasingly sophisticated analysis techniques that can detect subtle patterns or regularities that might indicate artificial origin. These methods must distinguish between genuine design features and the countless patterns that can emerge from natural processes operating under exotic conditions. Future discoveries may provide definitive answers to questions about the nature and origin of interstellar visitors, or they may deepen the mysteries surrounding these cosmic messengers. Either outcome would advance our understanding of the universe and our place within it, whether by revealing the diversity of natural processes operating throughout the galaxy, or by providing evidence that we are not alone in developing technological capabilities. The ongoing search for interstellar visitors represents one of the most profound scientific endeavours of our time. combining cutting-edge technology with fundamental questions about the nature of our cosmic environment. As detection capabilities continue to improve and new discoveries expand our understanding, we edge closer to answering whether these mysterious objects are simply exotic natural phenomena or something far more extraordinary. Tonight, in observatories scattered across the globe, sensitive instruments continue their patient watch for the next visitor from beyond our solar system. The discovery might come without warning, announced by automated systems that detect subtle changes in the positions of celestial objects captured in digital images. When that moment arrives, the global astronomical community will spring into action, coordinating observations and analyses designed to extract every possible insight from humanity's latest encounter with a messenger from the stars. The implications of such discoveries extend far beyond academic astronomy, touching on fundamental questions about the prevalence of life and intelligence throughout the universe. Whether the next interstellar visitor proves to be a chunk of ancient ice from a distant comet cloud, or something that challenges our understanding of what's possible in the cosmos, it will carry with it the potential to transform our perspective on our place in the vast community of worlds that populate our galaxy. In the quiet hours before dawn, as automated systems continue their systematic scan of the heavens, we wait for that next moment of discovery that could change everything we thought we knew about the universe around us. The stars hold their secrets, but with each passing night, our vigil brings us closer to unlocking the mysteries carried by these ancient wanderers from the depths of interstellar space. The mathematics of detection reveal themselves in the quiet precision of these nightly observations. Each telescope captures millions of individual measurements, comparing tonight's sky to yesterday's with accuracy that borders on the miraculous. At the Lowell Observatory's Discovery Channel telescope in Arizona, Dr. Nick Moskowitz describes the process with quiet fascination. We're essentially creating a time-lapse movie of the entire sky, he explains, where each frame is separated by hours or days. Anything that moves between frames becomes a candidate for further investigation. The challenge lies in distinguishing meaningful motion from the countless sources of apparent movement that plague astronomical observations. Satellites streak across images in predictable patterns, aircraft leave telltale trails, and even slight vibrations in telescope mounts can create the illusion of stellar motion. The algorithms that process these observations must account for atmospheric refraction, thermal expansion of telescope structures, and the subtle gravitational flexing that affects even the most stable observatory platforms. Dr. Robert McMillan, who pioneered many of the techniques used in modern sky surveys, describes the evolution of detection capabilities over the past 2 decades. When we started the Spacewatch program in the 1980s, he recalls, we were lucky to process a few hundred observations per night. Now our systems analyze millions of measurements automatically, flagging potential discoveries faster than human observers could even review the raw data. This acceleration in processing capability has transformed the timeline of interstellar object discovery. Where previous visitors like Oumuamua required weeks of careful analysis to confirm their extrasolar origins, future detections might be verified within hours of initial observation. The Rubin Observatory's alert system will be capable of identifying potential interstellar visitors and distributing notifications to observatories worldwide in less than 60 seconds. The precision required for these rapid confirmations pushes computational astronomy to its theoretical limits. Dr. Stephen Chesley from NASA's Jet Propulsion Laboratory specializes in the orbital mechanics calculations that distinguish between objects bound to our solar system and genuine interstellar travelers. The mathematics involved in these determinations require accounting for gravitational perturbations from all major planets, the subtle effects of solar radiation pressure, and even relativistic corrections that become significant for objects moving at extreme velocities. Recent advances in machine learning are augmenting these traditional analytical approaches with pattern recognition systems that can identify likely interstellar candidates before complete orbital solutions are available. Dr. Joachim Moyens from the University of Washington has developed neural networks that analyze the early trajectory measurements of newly discovered objects, predicting with remarkable accuracy which ones might prove to have hyperbolic orbits. These predictive systems are particularly valuable for objects discovered near the limits of detection, where only a few nights of observations might be available before they fade beyond telescope sensitivity. By identifying likely interstellar visitors early in their observational arc, astronomers can prioritize follow-up observations and coordinate international campaigns while objects remain accessible to detailed study. The international coordination required for these rapid response efforts operates through communication networks that span continents and time zones. The Minor Planet Center's alert system can distribute discovery notifications to hundreds of observatories simultaneously, while specialized software helps facility schedulers optimize telescope pointing to maximize observational coverage. Dr. Gareth Williams, who directs the Minor Planet Center, describes the challenge of coordinating global observations of rapidly moving targets. When we issue an alert for a potential interstellar object, he explains, observatories from Hawaii to South Africa begin adjusting their schedules within minutes. The goal is to ensure continuous tracking as Earth rotates, preventing gaps that could result in losing these fleeting visitors. The technological infrastructure supporting these coordination efforts includes dedicated communication satellites, redundant data networks, and automated translation systems that ensure observational instructions reach international facilities regardless of language barriers. The entire system operates with military-grade reliability, recognizing that the opportunity to study each interstellar visitor may never come again. Space-based detection systems add another dimension to this global surveillance network. NASA's NEOWISE mission continues to scan the sky in infrared wavelengths, providing thermal observations that complement visible light surveys from ground-based facilities. The space-based perspective eliminates atmospheric interference while accessing wavelength regions that reveal physical properties invisible to terrestrial telescopes. Dr. Amy Meinzer, who leads the NEOWISE science team, emphasizes how infrared observations can provide crucial insights into the composition and structure of interstellar visitors. Thermal measurements reveal details about surface materials, internal heat distribution, and outgassing processes that visible light observations might miss entirely. For future interstellar objects, these thermal signatures could provide definitive evidence of artificial construction if such objects exist. The proposed NEO Surveyor mission will dramatically expand space-based detection capabilities when it launches later this decade. With sensitivity improvements of several orders of magnitude over current systems, the mission could potentially detect interstellar visitors while they're still beyond the orbit of Jupiter, providing months of advance warning rather than the weeks currently available. This extended observation timeline would revolutionize interstellar object science by allowing comprehensive study campaigns to be planned and executed before objects reach peak brightness. Dr. Amy Meinzer describes mission concepts that would track visitors from initial detection through closest approach and back to the detection limits, providing complete characterization of their physical and chemical evolution as they respond to solar heating. The European Space Agency is developing complementary capabilities through their HERA mission and related planetary defense technologies. While primarily focused on asteroid deflection demonstration, these missions include navigation and imaging systems that could be rapidly reconfigured for interstellar object studies. The precision guidance required for asteroid operations translates directly to the challenges of tracking fast-moving visitors from other star systems. Dr. Patrick Michael, who coordinates ESA's asteroid research programs, points out how planetary defense technologies provide unexpected benefits for interstellar object science. The same autonomous navigation systems needed for spacecraft intercept missions can enable detailed tracking of objects moving at extreme velocities, while advanced imaging systems can resolve structural details that might distinguish between natural and artificial construction. The artificial intelligence systems being developed for these missions represent some of the most sophisticated autonomous spacecraft technologies ever deployed. Traditional space missions rely on detailed pre-planning and ground-based control, but the brief encounter times and communication delays associated with interstellar visitors require unprecedented levels of autonomous decision-making capability. Engineers at NASA's Jet Propulsion Laboratory are developing AI systems that can make real-time choices about observation priorities, instrument configurations, and trajectory corrections without waiting for commands from Earth. These systems must balance competing scientific objectives while adapting to unexpected discoveries or equipment failures during critical observation periods. Laboratory simulations of these autonomous operations push the boundaries of artificial intelligence research. The AI must process observations, recognize patterns, formulate hypotheses, and test predictions all within the compressed timescales of high-speed encounters. The challenge becomes particularly complex when considering multi-spacecraft missions that must coordinate their observations while operating independently. Dr. Steve Chien, who leads JPL's autonomous systems research, describes scenarios where spacecraft AI must make split-second decisions about which instruments to activate based on discoveries made moments earlier. If initial observations reveal unexpected characteristics, the system must rapidly reconfigure its entire observation strategy to maximize scientific return from the limited encounter time. The ground-based facilities that will identify future interstellar visitors are also benefiting from advances in autonomous operations. Modern survey telescopes operate with minimal human intervention, automatically adjusting their pointing, focus, and exposure parameters based on weather conditions, sky brightness, and target priorities. The Large Synoptic Survey Telescope, soon to be renamed the Vera C. Rubin Observatory, represents the pinnacle of these autonomous survey capabilities. The facility will operate essentially as a robotic observatory, making thousands of independent decisions each night about where to point, how long to expose, and which observations to prioritize based on real-time analysis of atmospheric conditions and scientific objectives. Dr. Stephen Kahn, who serves as the observatory's director, describes an operation that resembles science fiction more than traditional astronomy. The telescope will capture an image of the entire visible sky every few seconds, process that data automatically, and identify potential discoveries faster than human observers could even review the raw images. The entire process from observation to scientific alert happens without human intervention. This level of automation is essential for handling the data volumes that next-generation surveys will generate. A single night of observations will contain more information than most astronomers analyze in their entire careers, requiring automated systems that can identify the most interesting discoveries among billions of routine measurements. The machine learning algorithms that power these automated systems are trained on decades of astronomical observations, learning to recognize patterns that distinguish genuine discoveries from instrumental artifacts and measurement uncertainties. Dr. Lucian Walkowicz from the Adler Planetarium describes these systems as artificial astronomers that never tire, never lose focus, and never overlook subtle signals that human observers might miss. The training process for these AI systems involves exposing them to millions of simulated observations, including rare events like interstellar visitor transits that occur too infrequently in real data to provide adequate training examples. Computer simulations generate realistic observations of hypothetical interstellar objects with various compositions, trajectories, and physical characteristics. Dr. Lynn Jones from the University of Washington leads efforts to create these simulation databases, which must accurately model everything from telescope optics and atmospheric conditions to the gravitational dynamics of objects moving through the solar system. The simulations provide AI systems with experience analyzing scenarios they might encounter only once in actual observations. The validation of these AI systems presents its own challenges, since the rarity of interstellar visitors means that years might pass between opportunities to test detection algorithms against real targets. Researchers are developing alternative validation approaches using known solar system objects placed on artificial trajectories that mimic interstellar visitor characteristics. The citizen science community continues to play an important role in these validation efforts. Amateur astronomers worldwide contribute observations that help calibrate automated detection systems and verify the accuracy of AI-generated classifications. The distributed nature of these networks provides continuous monitoring across multiple time zones and weather patterns. Dr. Carrie Nugent from Olin College emphasizes how citizen science networks complement rather than compete with professional facilities. While major observatories excel at systematic surveys and detailed follow-up observations, amateur networks provide the continuous monitoring needed to track objects across extended periods and varying observational conditions. The technological capabilities available to amateur astronomers have improved dramatically over the past decade. Small telescopes equipped with sensitive CCD cameras and automated tracking systems can now detect objects that challenged professional facilities just a few years ago. Sophisticated software packages allow amateur observers to contribute calibrated measurements that meet professional research standards. The Unistellar network represents one of the most ambitious citizen science projects in astronomy, connecting thousands of small telescopes worldwide through cloud-based coordination systems. Dr. Frank Marshis from the SETI Institute describes a network that operates essentially as a distributed observatory, with individual telescopes contributing specialized observations to comprehensive research programs. This distributed approach provides capabilities that single large facilities cannot match. While professional telescopes must divide their time between multiple research programs, citizen science networks can dedicate extended periods to monitoring specific targets of interest. The result is unprecedented long-term coverage of astronomical phenomena that require continuous observation. The data analysis techniques developed for processing citizen science observations are finding applications throughout astronomy. Methods for combining measurements from instruments with different characteristics, calibration standards, and observational limitations are being adapted for studies of variable stars, exoplanet transits, and solar system dynamics. The educational impact of citizen science participation extends far beyond the immediate research contributions. Participants learn firsthand how scientific knowledge develops through careful observation and analysis, while contributing to discoveries that advance our understanding of the cosmos. Universities worldwide are incorporating citizen science projects into their curricula, allowing students to participate in active research while learning fundamental concepts in astronomy and data analysis. Dr. Laura Truel from Northwestern University describes educational programs where students contribute to professional research while developing critical thinking skills and scientific literacy. The public engagement aspects of interstellar visitor research have created unprecedented opportunities for science communication. The mysterious nature of these objects captures public imagination in ways that more routine astronomical discoveries cannot match, generating widespread interest in space science and astronomy. Planetariums and science museums worldwide have developed programs that allow visitors to explore the implications of interstellar visitor discoveries. Interactive exhibits let people analyze real observational data and draw their own conclusions about the nature of these cosmic messengers. Social media platforms have become important venues for sharing real-time updates about interstellar object discoveries and research developments. Professional astronomers use these channels to communicate directly with interested members of the public, fostering unprecedented transparency in the research process. Dr. Katie Mack from Perimeter Institute describes how social media enables scientists to share both their excitement about new discoveries and their uncertainties about interpreting complex observations. The public gets to witness the scientific process in real time, seeing how knowledge develops through careful analysis and peer review. The challenge lies in maintaining scientific accuracy while engaging public interest. The same mysterious properties that make interstellar visitors fascinating also make them susceptible to misinterpretation and sensationalism. Scientists must balance honest acknowledgement of uncertainties with responsible communication about what the evidence actually supports. The protocols being developed for communicating about potentially extraordinary discoveries draw lessons from previous controversies in astronomy and astrobiology. Clear distinctions must be maintained between observations, interpretations, and speculations, while ensuring that legitimate scientific discussions don't become distorted in public discourse. Dr. Seth Shostak from the SETI Institute emphasizes the importance of establishing clear criteria for evaluating extraordinary claims before such discoveries occur. The scientific community needs agreed-upon standards for what would constitute convincing evidence of artificial origin, along with procedures for independent verification and peer review. The development of these protocols involves not just astronomers and planetary scientists, but also experts in fields ranging from materials, science, to artificial intelligence. Distinguishing between natural and potentially artificial phenomena requires interdisciplinary expertise that spans multiple areas of scientific knowledge. The philosophical implications of discovering artificial interstellar objects would extend far beyond astronomy into questions about the prevalence and nature of technological civilizations throughout the galaxy. Dr. Sarah Seeger from MIT points out how such discoveries would fundamentally alter our understanding of our place in the cosmic community. Even if all future interstellar visitors prove to be natural phenomena, their study is revealing fundamental aspects of how planetary systems form and evolve throughout the galaxy. Each new discovery provides direct samples of material from alien star systems, offering insights into conditions that exist nowhere in our own solar system. The chemical compositions revealed through spectroscopic analysis of interstellar visitors are challenging theoretical models of planetary formation and evolution. Some objects display unusual ratios of elements that suggest formation around stars with very different properties than our Sun, while others show evidence of processing by physical conditions that don't exist in our local environment. Dr. Alan Stern from the Southwest Research Institute describes how these chemical signatures are expanding our understanding of the diversity of planetary systems throughout the galaxy. The unusual compositions observed in some interstellar visitors suggest that the processes we see operating in our own solar system represent just a small fraction of the phenomena that occur around other stars. The thermal properties of interstellar objects are providing additional insights into the physical conditions that exist in the outer regions of alien planetary systems. Observations of how these objects respond to solar heating reveal details about their internal structure, thermal conductivity, and volatile content that complement chemical analysis. Some visitors display thermal behaviors consistent with conventional rocky or icy compositions, while others show anomalous heating and cooling patterns that suggest more complex internal structures. Dr. Michael Kelly from the University of Maryland analyzes these thermal signatures to understand the formation and evolution history of interstellar objects. The possibility that some thermal anomalies might indicate artificial construction remains a subject of intense scientific debate. While most researchers favor natural explanations for unusual observations, the question of how to definitively distinguish between exotic natural phenomena and possible technological artifacts continues to challenge the astronomical community. Future space missions offer the possibility of resolving these questions through direct investigation of interstellar visitors. Sample return missions could bring material from other star systems back to Earth for comprehensive laboratory analysis, using techniques impossible with remote observations. Such missions would face unprecedented technical challenges due to the extreme velocities involved in interstellar encounters. Revolutionary advances in propulsion technology would be required to enable spacecraft to match velocities with targets moving at dozens of kilometers per second relative to the Sun. Solar sail technology offers one potential approach, using radiation pressure from sunlight to achieve the high velocities needed for intercept missions. Recent demonstrations have validated the basic principles, though scaling up to operational capabilities remains a significant engineering challenge. Dr. Les Johnson from NASA describes mission concepts that could achieve intercept velocities approaching those of typical interstellar visitors. Such missions would require sails kilometers in diameter deployed with unprecedented precision, but the fundamental physics appears sound, and the required materials are within reach of current technology. Nuclear propulsion systems provide another potential solution, offering the high specific impulse needed to match velocities with fast-moving targets. NASA's ongoing development of nuclear thermal and electric propulsion could eventually enable the Delta-V requirements for interstellar object intercept missions. The scientific return from such missions would be extraordinary, providing detailed characterization of materials from other star systems using the full range of laboratory analytical techniques. Isotopic analysis could reveal formation conditions with precision impossible from remote observations, while microscopic examination could detect structural details that might distinguish natural from artificial construction. The planetary protection challenges associated with sample return from interstellar objects would require developing entirely new containment and analysis protocols. Current procedures focus on preventing contamination between Earth and other bodies within our solar system, but material from alien star systems presents unknown risks that existing frameworks cannot address. Dr. Catherine Conley, formerly NASA's Planetary Protection Officer, has begun developing preliminary guidelines for handling interstellar samples. The protocols would likely require containment facilities more sophisticated than any currently existing, with multiple redundant barriers against release of potentially hazardous material. The scientific value of such samples would justify the extraordinary precautions required for their safe handling. Laboratory analysis could provide definitive answers to fundamental questions about planetary formation throughout the galaxy, the prevalence of organic chemistry in alien environments, and possibly even evidence for biological processes operating around other stars. The search for biological signatures in interstellar objects represents one of the most profound aspects of this research. While most scientists remain skeptical about the survival of living systems during million-year interstellar journeys, the possibility cannot be dismissed without careful investigation of organic chemistry within these cosmic visitors. Dr. Christopher McKay from NASA's Ames Research Center studies the potential for panspermia, the transfer of biological material between star systems aboard interstellar objects. Laboratory experiments are revealing surprising resilience in some biological systems under conditions that simulate interstellar space environments. The detection techniques being developed for identifying biological signatures push the boundaries of analytical chemistry. New spectroscopic methods can identify complex organic molecules at extremely low concentrations, while advanced imaging systems can detect microscopic structures that might indicate biological origins. Future observations with the James Webb Space Telescope and other next-generation facilities will provide unprecedented sensitivity for detecting organic chemistry in interstellar visitors. The infrared capabilities of these instruments can identify molecular species that are invisible to optical telescopes, potentially revealing biological signatures that previous observations missed. The implications of discovering biological material in interstellar objects would be profound, suggesting that life might be more widely distributed throughout the galaxy than previously imagined. Such discoveries would also raise fundamental questions about the interconnectedness of biological evolution across vast regions of space. Even the detection of complex organic chemistry without clear biological signatures would be significant, indicating that the chemical precursors for life are common throughout the galaxy. Dr. Scott Sanford from NASA's Ames Research Center studies how organic molecules form and evolve in interstellar environments, providing context for interpreting chemical signatures in visiting objects. The laboratory synthesis of organic compounds under simulated interstellar conditions is revealing pathways for complex chemistry that don't require biological processes. These studies help establish baselines for distinguishing between organic molecules produced by non-biological chemistry and potential biosignatures that might indicate living systems. The interdisciplinary nature of interstellar visitor research brings together expertise from fields ranging from astronomy and planetary science to chemistry, biology, and materials science. No single discipline possesses all the tools needed to fully characterize these cosmic messengers and interpret their implications. Dr. Jennifer Eigenbrode from NASA's Goddard Space Flight Center emphasizes how organic geochemistry techniques developed for Mars exploration are being adapted for interstellar object studies. The methods used to detect and analyze organic compounds in Martian rocks provide templates for investigating similar chemistry in visitors from other star systems. The technological advances driven by interstellar visitor research are creating new capabilities that benefit many areas of space science and astronomy. High-precision navigation systems, autonomous spacecraft operations, and rapid response mission architectures all have applications beyond the study of interstellar objects. The data analysis techniques developed for identifying rare objects among billions of routine observations are finding applications in other areas of time domain astronomy. Machine learning algorithms trained on interstellar object detection are being adapted for identifying supernova, gravitational wave counterparts, and other transient phenomena. The international cooperation frameworks established for interstellar object research serve as models for other large-scale scientific collaborations. The protocols for rapid data sharing, coordinated observation campaigns, and real-time analysis are being adopted by research programs studying diverse astronomical phenomena. The economic implications of interstellar visitor research extend beyond the immediate scientific returns. The technological developments driven by these studies have potential applications in areas ranging from satellite navigation to autonomous vehicle systems, creating economic value that justifies the research investments. The inspiration generated by interstellar visitor discoveries is also driving increased interest in science, technology, engineering, and mathematics education. Students worldwide are motivated by the possibility of discovering artifacts from alien civilizations or samples of exotic chemistry from distant star systems. Universities report increased enrollment in astronomy and planetary science programs following major interstellar object discoveries. The mysterious nature of these visitors captures student imagination, in ways that more routine scientific topics cannot match, potentially inspiring a new generation of researchers. The long-term scientific legacy of interstellar visitor research will likely extend far beyond the specific questions about individual objects. The techniques developed for detecting and studying these rare cosmic messengers are advancing our capabilities for investigating the broader population of small bodies throughout the solar system. The systematic sky surveys designed to find interstellar visitors are also discovering thousands of ordinary asteroids and comets, contributing to our understanding of solar system formation and evolution. The same detection algorithms that identify visitors from other stars are revealing the diversity of objects that populate our own cosmic neighborhood. As we continue our patient vigil for the next interstellar visitor, the global network of telescopes, computers, and dedicated researchers stands ready to respond to whatever cosmic messenger appears next. The discovery might happen tonight, next week, or next year, but when it comes, humanity will be prepared to extract every possible insight from our brief encounter with another sample of the galaxy beyond our solar system. The quiet revolution in astronomical capability continues each night as automated systems scan the heavens with sensitivity and precision that would have seemed impossible just a generation ago. Behind every image captured, every object detected, and every discovery confirmed lies a complex web of technology, expertise, and international cooperation that represents one of humanity's most ambitious scientific endeavours. In the end, whether the next interstellar visitor proves to be a conventional chunk of alien ice, or something that challenges our understanding of what's possible in the universe, it will carry with it the potential to transform our perspective on our place among the stars. Each discovery reminds us that we are part of something much larger than ourselves, connected to other worlds through the vast networks of matter and energy that flow between star systems across the galaxy. The search continues tonight in observatories around the world, where sensitive instruments maintain their patient watch for subtle signs of movement against the stellar background. Somewhere in the darkness beyond our solar system, the next cosmic messenger might already be approaching, carrying within its ancient structure new mysteries for humanity to unravel and new insights into the nature of the universe we call home. The machines never sleep. Tonight, as you settle into quiet moments before rest, arrays of silicon eyes are drinking in starlight from across the Pacific, their sensors cooled to temperatures that would freeze your breath solid. In Chile's Atacama Desert, where the air holds less moisture than the surface of Mars, robotic telescopes sweep methodically across the southern sky. Each exposure captures light that has travelled for years just to reach these waiting detectors, and buried within that ancient radiance might be something extraordinary. Somewhere out there, perhaps already within the gravitational embrace of our Sun, an object carries the dust of alien worlds. It moves with the patience of geological time, yet with velocities that mock our earthbound understanding of speed. The question isn't whether another visitor will come. The question is whether we'll recognise it when it arrives. The story of our cosmic watchers begins with mathematics so precise it borders on the mystical. Dr. Marco Micheli at the European Space Agency's Operations Centre describes the challenge with quiet reverence. When you're tracking something moving at 40 kilometers per second, he explains, the difference between discovery and loss often comes down to measurements accurate to fractions of an arc second. That's like detecting the width of a human hair from 2 miles away. These calculations unfold in real time across continents. The Catalina Sky Survey in Arizona processes roughly 15,000 observations each clear night, while the Panoramic Survey, Telescope and Rapid Response System in Hawaii captures 4 times that number. Each measurement feeds into algorithms that can distinguish between the predictable ellipses of solar system natives and the telltale hyperbole that betray visitors from the void. The mathematical elegance masks an almost overwhelming technical challenge. Dr. Robert Werrick, whose sharp eyes first spotted the needle in the cosmic haystack we came to know as Oumuamua, describes the moment of recognition with characteristic understatement. "You run the orbital calculations several times," he recalls, "because your first instinct is that something must be wrong with the data. Objects simply don't move through our solar system at those angles and velocities unless they're coming from somewhere else entirely." That realization, when it comes, transforms routine observations into something approaching revelation. Within hours of confirming an interstellar trajectory, alert systems activate across the global astronomical community. Telescopes in Chile receive coordinates and begin tracking. Facilities in Hawaii adjust their schedules. Observers in Australia prepare for the object's passage across their portion of sky. The entire planetary network of watchers focuses on a single point of light racing through the darkness. The European Southern Observatory's very large telescope complex represents perhaps the most sophisticated, ground-based system for studying these fleeting visitors. Dr. Olivier Hainaut, who led some of the most detailed observations of previous interstellar objects, explains how modern facilities can extract extraordinary detail from incredibly faint targets. "We're essentially doing forensic astronomy," he notes. "Each photon carries information about materials that formed around stars we'll never visit under conditions we can barely imagine." The forensic analogy proves apt when considering the detective work required to characterize these objects. Spectroscopic analysis reveals chemical fingerprints that tell stories of alien chemistry. Photometric monitoring tracks changes in brightness that hint at rotation rates and surface properties. Thermal observations map how objects respond to solar heating, revealing internal structures invisible to optical light. Recent advances in machine learning are accelerating this analytical process dramatically. Neural networks trained on millions of astronomical observations can now identify potentially interesting objects within minutes of detection, rather than the hours or days previously required for human analysis. Dr. Mario Jurich at the University of Washington, who oversees data processing for the upcoming Rubin Observatory, describes systems that will generate more candidate detections in a single night than the entire astronomical community currently processes in a month. The Rubin Observatory itself represents a quantum leap in detection capability. When fully operational, its combination of large mirror, wide field of view, and sensitive cameras will photograph the entire southern sky every few nights for a decade. Computer models suggest this systematic approach could detect 50 to 100 interstellar visitors annually, compared to the handful discovered so far. Dr. Željko Ivezic, the observatory's director, speaks of this future with measured excitement. For the first time, he explains, we'll have comprehensive statistics on interstellar objects. We'll understand their size distribution, compositional diversity, and arrival patterns. Most importantly, we'll be able to identify truly anomalous objects against a background of normal interstellar wanderers. The question of what constitutes anomalous touches on one of the most contentious debates in contemporary astronomy. Dr. Abraham Loeb from Harvard University continues to argue that some interstellar visitors display characteristics that challenge conventional explanations. The acceleration observed in Oumuamua, the unusual dust-to-gas ratios seen in some objects, and trajectory patterns that seem inconsistent with random arrival all warrant serious consideration of non-natural origins. The scientific mainstream remains largely skeptical of artificial hypotheses, but researchers are working to establish objective criteria for evaluating such possibilities. Dr. Jason Wright at Penn State University has proposed specific observational tests that could distinguish between natural formation processes and possible technological construction. These include geometric shapes optimized for specific functions, surface compositions inconsistent with known geological processes, and behavior patterns that cannot be explained by conventional physics. Future space missions may provide definitive answers to these questions through direct investigation. The European Space Agency's Comet Interceptor mission, currently in development, could potentially be retargeted toward newly discovered interstellar objects. Such encounters would require revolutionary advances in autonomous navigation and high-speed observation techniques, but they could provide close-up characterization impossible from ground-based telescopes. NASA's concept studies for rapid response interstellar visitor missions envision spacecraft pre-positioned in the outer solar system, ready for launch toward promising targets within days of discovery. Nuclear propulsion systems could provide the velocity changes needed to match course with objects moving at extreme speeds, enabling extended observation periods rather than brief flybys. The technological challenges are formidable, but the potential scientific return justifies the investment. Direct samples of interstellar material could reveal isotopic signatures that pinpoint stellar origins, chemical compositions that indicate formation conditions, and structural details that might distinguish between natural and artificial construction. Laboratory analysis of such samples would require developing entirely new containment and handling procedures. Dr. Catherine Conley, formerly NASA's Planetary Protection Officer, has begun outlining protocols for studying material that originates beyond our solar system. The procedures would likely require facilities more sophisticated than any currently existing, with multiple redundant barriers against contamination. The possibility of biological material within interstellar objects adds another layer of complexity to these considerations. While most scientists remain skeptical about organisms surviving million-year journeys through the radiation environment of interstellar space, the question cannot be answered without careful investigation. Dr. Christopher McKay from NASA's Ames Research Center studies the potential for panspermia, the transfer of life between star systems. Laboratory experiments reveal surprising resilience in some biological systems under simulated interstellar conditions, suggesting that the possibility, however remote, deserves serious scientific attention. The detection techniques being developed for identifying biological signatures push analytical chemistry to its limits. New spectroscopic methods can identify complex organic molecules at extremely low concentrations, while advanced imaging systems can detect microscopic structures that might indicate biological origins. The James Webb Space Telescope provides unprecedented capabilities for this type of analysis. Its infrared sensitivity can detect molecular species invisible to optical telescopes, while its spectroscopic precision can distinguish between organic molecules produced by biological and non-biological processes. Ground-based facilities are also being upgraded specifically for interstellar object studies. The extremely large telescope under construction in Chile will have light-gathering power more than 10 times greater than current facilities, enabling detailed spectroscopic analysis of even the faintest visitors. These technological advances are occurring alongside developments in artificial intelligence that promise to revolutionize how we identify and study interstellar objects. Machine learning systems are being trained to recognize subtle patterns in observational data that might escape human notice, potentially identifying artificial signatures or biological markers that would otherwise remain hidden. The citizen science community plays an increasingly important role in these efforts as well. Networks like the Interstellar system connect thousands of amateur astronomers worldwide, providing distributed observation capabilities that complement professional facilities. These networks have already demonstrated their value by successfully tracking faint interstellar visitors that challenge even large telescopes. Dr. Frank Marquis from the SETI Institute coordinates many of these citizen science efforts, developing software that allows amateur observers to contribute calibrated measurements to professional research programs. The distributed nature of these networks provides continuous monitoring across multiple time zones and weather patterns. The international cooperation required for studying interstellar visitors operates on an unprecedented scale. When objects are discovered, observatories across 6 continents coordinate their efforts to maximize scientific return from brief observation windows. The Minor Planet Center serves as the global clearinghouse for these observations, collecting data from dozens of facilities and maintaining official records of confirmed interstellar objects. Dr. Gareth Williams, who directs the center, describes coordination challenges that span language barriers, time zones, and varying levels of technological sophistication. The goal, he explains, is ensuring that no potentially significant observation is lost due to communication failures or scheduling conflicts. The philosophical implications of discovering artificial interstellar objects extend far beyond astronomy into fundamental questions about the prevalence of technological civilizations throughout the galaxy. Dr. Sarah Seeger from MIT points out how such discoveries would alter our understanding of our place in the cosmic community, potentially providing evidence that intelligence and technology represent common developments in planetary evolution. Even if all future interstellar visitors prove to be natural phenomena, their study is revealing aspects of planetary formation and chemical evolution that exist nowhere in our own solar system. Each visitor carries direct samples of materials from alien stellar environments, providing insights into conditions that theoretical models can only approximate. The thermal properties revealed through infrared observations are particularly intriguing. Some objects display heating and cooling behaviors consistent with conventional compositions, while others show anomalous thermal responses that suggest complex internal structures or analyzes these thermal signatures to understand formation and evolution processes operating around different types of stars. The diversity observe unusual material properties. Dr. Michael Kelly from the University of Maryland so far suggests that planetary system formation involves a much wider range of conditions and outcomes than our own solar system represents. The chemical compositions revealed through spectroscopic analysis are equally diverse. Some visitors show evidence of water ice and organic compounds, suggesting formation in cold outer regions similar to our Kuiper belt. Others display unusual elemental ratios that indicate formation around stars with very different properties than our Sun. Dr. Bin Yang from the European Southern Observatory has spent years developing techniques for extracting chemical information from the faint light reflected by these distant objects. The challenge lies not just in detecting specific molecules, but in understanding how materials formed under alien conditions might behave during their passage through our solar system. The morphological studies enabled by high-resolution imaging add yet another dimension to our understanding. The Hubble Space Telescope has provided detailed views of dust comas and nuclear structures that reveal complex evolutionary processes occurring as objects respond to solar heating. Some visitors develop the bright comas and tails characteristic of conventional comets, while others remain stubbornly inactive despite receiving intense solar radiation. These differences provide clues about internal composition and structure that complement chemical analysis. The rotation states of interstellar objects present their own puzzles. Some tumble chaotically, suggesting violent ejection from their parent systems, while others maintain stable rotation that implies gentler formation or subsequent processing during their interstellar journey. Dr. Alan Stern from the Southwest Research Institute emphasizes how these rotational characteristics provide insights into the dynamical processes that eject objects from planetary systems. The tumbling observed in Oumuamua, for example, suggests collision or tidal disruption rather than gradual orbital decay. The statistical properties of interstellar visitor trajectories are beginning to reveal patterns that constrain models of galactic dynamics and stellar encounters. Rather than arriving from random directions, some objects appear to originate from specific regions of the galaxy, suggesting that ejection processes might be more directional than previously assumed. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy specializes in tracing these trajectories backward through millions of years of galactic motion. The calculations require accounting for gravitational perturbations from countless stars, each of which has moved through space during the object's long journeys. These trajectory analyses sometimes identify potential parent star systems, though the uncertainties involved make definitive associations extremely difficult. The possibility that we might eventually trace specific visitors back to their stellar origins adds urgency to current detection efforts. The discovery rate of interstellar objects appears to be accelerating as detection systems improve and survey coverage expands. This increasing frequency suggests that such visitors might be far more common than initial estimates indicated, with implications for our understanding of planetary system evolution throughout the galaxy. Statistical models based on current detection rates suggest that dozens of interstellar objects might pass through the inner solar system annually, most too faint or inactive to detect with current surveys. The next generation of facilities will have the sensitivity to find much smaller and darker visitors, potentially revealing the true scope of interstellar traffic through our cosmic neighborhood. The implications of discovering a large population of interstellar visitors extend beyond astronomy into astrobiology and the search for life elsewhere in the galaxy. These objects represent direct samples of materials from planetary systems throughout our galactic region, carrying information about chemical compositions and possibly biological signatures from worlds we may never visit directly. The possibility that some visitors might be artificial adds another dimension to these considerations. If technological civilizations are common in the galaxy, they might use interstellar probes to explore nearby star systems, much as we plan to study other stars with future space missions. The protocols being developed for responding to potentially artificial visitors draw on frameworks established for traditional CT research, but they must address the unique challenges posed by physical objects rather than electromagnetic signals. Unlike radio transmissions, which provide warning of their approach, interstellar objects appear suddenly and remain accessible for only brief periods. The International Academy of Astronautics has begun developing guidelines for responding to potentially artificial interstellar visitors, addressing questions about evidence standards, information sharing, and attempts at communication or investigation. These protocols recognize that such discoveries would have profound implications for humanity's understanding of its place in the universe. The technological spillovers from interstellar visitor research benefit many other areas of astronomy and space science. High-precision astrometry techniques developed for tracking fast-moving objects improve asteroid and comet studies. Machine learning algorithms trained on interstellar object detection enhance searches for supernova and other transient phenomena. The international cooperation frameworks established for coordinating rapid response observations serve as models for other time-critical astronomical research. Communication protocols and data-sharing agreements developed for interstellar visitor studies are being adopted by programs investigating gamma-ray bursts, gravitational wave counterparts, and exoplanet transits. The educational impact of interstellar visitor research extends far beyond professional astronomy. Universities worldwide incorporate these discoveries into curricula that demonstrate how scientific knowledge develops through careful observation and analysis. Students follow the entire process from detection through characterization, learning firsthand about hypothesis testing and evidence evaluation. The next interstellar visitor is already out there, somewhere in the darkness between stars. Tonight, as automated systems continue their silent vigil across observatories worldwide, that ancient wanderer might cross the threshold of detection, its faint light finally reaching sensors that have waited years for this moment. When it happens, the discovery will unfold not with fanfare, but with the quiet precision of mathematics and the patient dedication of scientists who understand that the universe reveals its secrets only to those willing to watch and wait. Whether that visitor carries the familiar chemistry of distant ice and rock, or something that challenges everything we thought we knew about what's possible in the cosmos, it will represent another thread in the vast tapestry connecting worlds across the galaxy. Each discovery reminds us that we are not isolated observers in an empty void, but participants in something far grander than ourselves, connected to other star systems through networks of matter and energy that span unimaginable distances and timescales. So tonight, as you rest, know that the search continues. In the quiet hours before dawn, sensitive instruments maintain their watch for the subtle signs of movement that would herald another messenger from the stars. The next chapter in humanity's encounter with the galaxy beyond our solar system might already be unfolding, waiting only for the right combination of starlight, silicon, and human curiosity to bring it into focus. And when that moment comes, we'll be ready to listen to whatever story this cosmic visitor has travelled so far to tell us.